I'll just write it here. So we'll say, all right, d squared y by dt squared plus dy by dt plus 2y equals 5 cosine t plus 30 degrees. Like that. All right, this was the problem I started to do the other day, except I added the 5 cosine t plus 30 degrees, right? What I just did was I set it equal to a constant. Now I'm going to make it a little bit harder. And I'm going to say I got initial conditions that y of 0 is equal to 0, and y prime of 0 is equal to 1. So y prime means the derivative, right? So I've got those two sets of results. All right. I said there's 3 steps in this process, right? What's step 1? Find my transient solution, which means solve which equation? Solve for the homogeneous equation. So what's the difference? What kind of equation is this, the one that's up there right now? Not particular. Second order. What kind of equation is it, though? Non-homogeneous, right? If it's equal to something other than 0, it's called a non-homogeneous. One thing that's really important about this, one thing I will hammer you guys on if you get this wrong, I used to hammer people on this in circuits when I teach it. Notice that all of the coefficients on the y term, so on the second derivative term, first derivative term, and the non-derivative term there, all of those are positive. They have to be positive. In a physical sense, they always have to be positive. Now, this is not a class where we're going to deal with, this is not an engineering class per se. This is much more of a mathematics-related class, right? So this isn't circuits. But if you had a circuit problem and you had negative coefficients on those terms, that's physically impossible. Why is that physically impossible?
You couldn't have a negative.
So what's going to happen is I would get an e to the positive number t. Can I ever have e to the positive number t? So that e to the something t represents the voltage on a capacitor, right? If the voltage on a capacitor is related to the energy stored in that capacitor, how much energy is going to be stored in that capacitor if I have a positive exponent? It's going to become infinite. That's more than God said there is in the universe, right? That's not possible, right? So in other words, you better always have negatives in those exponents. In other words, your transient solution better always do what? Better always go away. And so convergence, I guess, is the best mathematical way to say that. In other words, that transient response always better decay over time. If it doesn't, you know you did something wrong. All right? There's no way in any physical sense that can happen. All right? So we always have positive coefficients. If you don't have positive coefficients, you've got a problem. All right? And that's a pretty critical thing to understand. You should have some understanding that solutions should decay to 0 and not blow up. Okay? All right. Anyway, so step 1 is my transient response. Okay? So for that, I guess that my solution must be C e to the st, and I plug that into the homogeneous equation. Okay? So I plug that into the equation d squared y dt squared plus d, and I'll write it as y sub c, right? 2y sub c equals 0. So I plug that guy in there, and without going through that, you guys already sort of know what's going to happen. If I take the derivative of e to the st, what comes out of that? S times e to the st. So if I take the derivative twice, I get s squared, right? So I'm going to have an e to the st term all over the place in this. And I should end up with s squared times e to the st plus s times e to the st plus 2e to the st all times c. All right? Now the thing I didn't specify up here is what should be true about c? Can't be 0. That would be a dumb choice, right? In other words, then I'm choosing that my answer is 0. And I know there has to be something. right? So I see I've got an e to the st term everywhere. So that just cancels out because I know that e to the st can never be what? 0. Right? So I get this thing that we call our characteristic equation. S squared plus s plus 2 equals 0. Okay? Now you guys know that there's 3 types of responses to this thing. There's actually 4, I guess. Right? But what are the 3 types of responses that you know when you have a second order equation? Damped, underdamped, critically damped. Critically damped is stupid. It will never happen in the real world. Okay? It'll never ever happen because it requires really, really precise values about resistors and capacitors and things like that. And it's not ever going to happen. So the 2 that happen are underdamped and overdamped. All right? In the case of underdamped, that's the tricky one. All right? That's what I have here. All right? How do I know that I have an underdamped? I have imaginary roots. And how can you see right away that that's got imaginary roots? Yeah, so basically to solve this thing, I know that I need to go to the quadratic formula, right? So I get the quadratic formula is what? So in general, it's the opposite of b plus minus b squared minus 4ac over 2a. All right, so I have that result. So if I look at that, I can see right away that b squared minus 4ac is negative. All right, so that tells me I got complex roots right off the bat. All right, so to solve that problem, what I do is I go straight to Matlab, my favorite solution tool, right? And so I write in here for this equation, I have a equal to 1, b equal to 1, c equal to 2. And then I go ahead and I write these guys in there like that. Okay? And then what I do again is I go, all right, I'm going to evaluate that selection. Oops. Evaluate that selection. Pop up my command window to look to see what I got. All right, so I got S1 equals this guy, and S2 equals that guy. So what I'm going to do is I'm going to see if I can take that out for now. And put that back over here. Sort of there, but it's small. There we go. All right. So I've taken S1 and S2 and I've written them there in case I want to use them later. Okay? All right, what do I do next? First of all, so what does that tell me at this point about what my transient solution is? Y sub c of t equals what at that point? So I'm going to say C1. C1 equals e to the S1 t plus C2 e to the S2 t. Technically all times u of t. Right? Now, so I ain't gonna plug in that whole ugly complex number because I know that if I write complex numbers over and over again like that, I'm only gonna make mistakes. So I'm gonna leave it as S1, right? Because that I know I'm gonna write cleanly. All right, I'm gonna leave it as C1 and C2, like that. All right, so I'm done with the transient response at this point, except that I don't know C1 and C2, but I can't get C1 and C2 until when? So I get the particular. So step 2 is to get the particular. So step 2 is find yp. All right? So back to the original equation. All right? This was our original equation up there. All right, now, how should I approach trying to get the particular solution to this guy? Complex exponentials. In particular, I can say that 5 cosine t plus 30 is what? All right, so you guys are going right to telling me the complex exponential. But it's not the complex exponential, it's what? The real part. All right, so it's the real part of 5 e to the j 30 degrees times e to the j t, like that. Okay? So knowing that, what do I guess is my particular solution? I'm going to guess a complex exponential again, but it's not just a complex exponential that I guess, right? It's got to be the real part of what? In this case, I'm going to say b e to the j phi e to the j t. So if I wrote that out as a cosine, what would that be?
B cosine t plus phi.
T plus phi. So the frequency hasn't changed. Frequency, the input and the output are the same. Phase has changed. So the angle has changed and the amplitude has changed. Okay? All right, so I plug that in to my equation, except what I do is if my output is a real part and my input is a real part, I can just forget the whole real part business and just plug in the exponentials. And then at the end, just take the real part of the result that I get. All right, so let's do that. So the equation I had was dyp squared dt squared plus dyp dt plus 2yp equals 5 e to the j phi e to the j t. Okay, in other words, I'm dropping the real part stuff. And I'm going to plug in this guy right now for my y sub p, and then remember that I have to take the real part at the end. All right, now, so let's think about this. My b and e to the j phi, do either of those depend on time? No. All right, the amplitude and the phase don't ever depend on time. But e to the jt does depend on time. Okay? If I have e to the at, okay, where a could be anything, what's the derivative of e to the at? A e to the at. What's the derivative of a? What's the second derivative of e to the at?
A squared.
A squared e to the at. Okay? So the only thing I got to take the derivative of in this case is e to the jt. It's like a is equal to j. Okay? So what I'm going to do is I'm going to skip the derivative here in the interest of time. And I'm going to say that I got j squared times e to the times b e to the j phi e to the jt plus j b e to the j phi e to the jt plus 2 b e to the j phi e to the jt is equal to 5 e to the j phi e to the jt. All right, what do I see from that right off the bat?
It's with the e to the jt and everything.
E to the jt everywhere. That goes away. And then I got a b e to the j phi throughout. I'll get to your question in a sec. So I'm going to write this guy as b e to the j phi times, all right, so basically I got j squared plus j plus 2 equals 5 e to the, oh, I wrote j phi over here. That should be j 30. No. In other words, I wrote that side wrong. E to the j 30 degrees, like that. Okay. Was that the question you had? Okay, so I thought. All right, so if I had this term that's left here, right? What do I know about j squared? It's -1. So I can write this whole guy as b e to the j phi, and this becomes -1 plus 2 plus j equals 5 e to the j 30 degrees. Okay? Now, this is, so the question was asked at the beginning of class about problem 1 and how I did problem 1 in the homework, or how I did it in Matlab. So I'm going to go back for a minute, and I'm just going to say that this was my frequency right here is omega equal to 1. So I'm going to write this guy in a general sense for a minute. I'm going to say I got b e to the j phi. That's minus 1. In other words, if I did this in a general sense, it's not liking me here. Go back. There we go. If I do this in a general sense, minus omega squared plus 2. Actually, I'm gonna confuse you guys if I do that. I still want to address the question that was asked, but I'm not going to keep this general. Come on. All right, it's supposed to let me. There we go. All right. I'll write this guy as 1 plus j equals 5 e to the j 30 degrees, like that. Now, how many equations is that? It's 2, right? If I take the magnitude of both sides, so let's do that first. Let's take the magnitude of both sides. What's the magnitude? So I got one equation for the magnitude and one for the angle. Okay? So let's do the magnitude first. We don't know b, right? The magnitude of b is b. Okay? What's the magnitude of e to the j phi? 1. Has to be 1, right? And then what's the magnitude of 1 plus j? Square root of 1 plus 1. All right? Real part plus imaginary part squared. What about over here? 5. Right? Because again, e to the j 30, e to the j anything has a magnitude of 1. Okay? So basically what I have is that b equals 5 over the square root of 2. Okay? Now over here, what do I have for the angle? Right? If I do the angle, what do I get?
35 plus 45 equals 45.
Well, so let's be careful. I got angle of b plus phi plus the angle of this guy. So the angle of this guy, I'm just going to say is arctan, you're right, it's 45 degrees, right? Arctan of 1 over 1, which is 45 degrees, equals what? 30 degrees. All right? So basically I get now that, what's the angle of b? 0. All right? So I get phi equals 30 minus 45 or minus 15 degrees. All right? So at this point I've got my result. All right? Now, this is one of those ones that, again, what did I do? I did this in Matlab. All right? And I just basically took this equation right here and I put it into Matlab to try to get the results. All right? And in fact, the way that I did it, let's take a quick look. The way that I did it is I basically said, I left everything in terms of omega. Right? And so I have my magnitude here. I've got my angle here. And I plugged in omega equal to 1. All right, to get that. All right, so I left it in that context. All right. Anyway, let's keep going here. So, all right. So now I know. Now I have my particular solution. My particular solution is the real part of 5 over square root of 2 e to the j minus 15 degrees times e to the jt, or how else can I write that? How should I really write that?
5 over square root cosine.
Yep, 5 over square root of 2 cosine t minus 15 degrees, like that. Okay? So, all right, I've got that result all kind of worked out at this point. Now what do I got to do?
Put them together.
Put them together, right? So this is my step 3, my total solution. All right, so I got y0 equals 0, and I was told that the first derivative at time t equal to 0 is equal to 1. Okay? All right, so let's do this. I've got yp equals C1 e to the S1t plus C2 e to the S2t plus, and that's, well, it's the whole thing. It does not want to work for me here with my eraser. It does not. Really doesn't want me to erase. All right, so I have y equals that time plus 5 over square root of 2, and I'm going to be lazy because I don't like this. I'm going to be specifically lazy because I want to do this in Matlab. I'm just going to call this guy b cosine of t plus phi. Okay? Now, what else do I have to do? I got to take the derivative, right? So y prime, the first derivative would be what? Yeah, S1 C1 e to the S1t plus S2 C2 e to the S2t. All right, now I got a cosine here. What's going on with cosine? What's the derivative of cosine? Negative sine. So I get negative b sine t plus phi. Okay? All right, now I'm worried about these things at time t equal to 0. So y of 0 is equal to 0. If I plug in t equal to 0, what happens to the exponentials? They go away, right? So I get C1 plus C2 plus what? So what is that? Yeah, so b, I'm going to call it b cosine phi. All right, and then that basically means I've got an equation that comes from this that I'm going to write as C1 plus C2 equals minus b cosine phi. And then I've got my other result that says the first derivative has an initial value of 1. So I write that as what? What's that equal to? At time t equal to 0, what's this first derivative equal to? Yeah, S1 C1 plus S2 C2 minus b sine phi. Okay? So that tells me my other equation is S1. Why it's not working? S1 C1 plus S2 C2 equals 1 plus b sine of phi. All right, so what am I going to do at this point? I'm going to put that into Matlab using that linear equation solving approach that I did before. So I'm going to write this in matrix form. All right, so in matrix form, if I have these two equations, I write the first equation's coefficients across the top row of my matrix. The things I'm solving for are C1 and C2. Okay, so I write 1, 1, and then S1, S2. Okay, so just to remind ourselves, if I expand this out, what I do is I multiply this row by this column first. So that would give me C1, so 1 times C1 plus 1 times C2. And then I would do this row with this column. That gives me SC1 times, or sorry, S1C1 plus S2C2. All right, and that has to be equal to the things I have here. So minus b cosine phi and 1 plus b sine phi, like that. Okay, so this is in matrix form ax equals b, where a is 1, 1, S1, S2, and x is the C1, C2, and b is our minus b cosine phi 1 plus b sine phi, like that. Okay? All right, so I put that into Matlab, and I have that over here. Okay? So let's look at my A. My A is 1, 1, semicolon, S1, S2. Right? The semicolon gives me a new line. And then I say minus b times, so this is the b vector here, minus b times cosine phi, and notice I have that pi over 180 to convert from radians to degrees. Then I have a semicolon to go to another line. Okay? And then to solve for the x, so the x was this guy over here. To solve for x, I have this line right here, so I say the inverse of a times b. So I'm going to highlight all of this code right here. And then I'm going to evaluate this selection. And here's my results. Okay? So I'm going to write down a couple of things for myself right now. So S1, I know I put that up top, but I'm going to put it here again. So it's minus 0.5 plus j times 1.3229. And then S2 equals minus 0.5 minus j times 1.3229. Okay? Now, the other thing I care about here is, I guess, my C1 value. So my C1 was the first line of the x vector. My C2 is the second line of the x vector. So let's write those down. C1 equals negative 1.7075 plus 0.6133j. And my C2 equals negative 1.7075 minus j times 0.6133. All right, now back to my manipulations here. All right, so the two equations were up here. Let's take my y, and I'm going to try to paste it here. All right, like so. And I want to focus for now just on this guy. So I have C1. Let's plug everything in here. So I get negative 1.7075 plus 0.6133j. Put that j in front. All right, that's my C1. Then I'm going to write e to the S1t. Now I'm going to plug in my S1 value now. And I'm going to say that this is negative 0.5 plus j times 1.3229t. Then I'm going to say plus C2. So C2 is negative 1.7075 minus j times 0.6133 e to the S2t. So that becomes, in this case, I'm going to write this as negative 0.5t minus j times 1.3229t. All right, now this is what I have here. At least it's this part of it, right? So a couple of things that I'm going to notice here. I have an e to the negative 0.5t in both terms. Okay, I'm going to factor that out. So I'm going to say that I've got e to the negative 0.5t times. Now, at that point, what I'm going to try to do is I'm going to try to group some like terms as best I can. So I'm going to take the terms that don't have the j in them. So terms that without a j in them. So in other words, not this term and not this term. I'm going to group those together. So I got negative 1.7075. Okay. And then it looks like I have one term with that over with this guy and one term with this over with this exponential. So I'm going to write this as negative 1.7075 times e to the j 1.3229t. And then I see that I have another term with a negative 1.7075. So I'm going to write that guy as plus e to the minus j 1.3229t, like that, okay? All right, you guys see what I did there? Basically, I took the terms with the negative 1.7075 in both this term and in this term and grouped them together. Now I'm going to do the same thing with that 0.6133. And in this case, what I'm going to do is I'm going to say plus 0.6133j, okay, times e to the j 1.3229t minus e to the minus j 1.3229t, like so. And I put a big bracket around all of it because I factored out the e to the negative 0.5t here. Okay? So one thing you notice about the real parts of the S1 and S2 is the real parts tell me basically they lead to a decay. The imaginary parts lead to sines and cosines. Okay? So let's keep going with that and see if we can see where that kind of comes from. All right, now when I look at this expression right here, all right, I need to remember a couple of things. The big thing that I need to remember, I'm going to write this down a little bit lower. Cosine of theta, we said was 1/2 times e to the j theta plus e to the minus j theta. And sine of theta was equal to 1/2 times 1 over j times e to the j theta minus e to the minus j theta, like that. It looks like I have, at least over here, it looks like I have something very similar to the cosine term. That looks like a minus here, but this was a plus. Okay. So what I can see here is if I clearly have an e to the j something t plus e to the minus j something t. That's very similar to this, except I don't have that 1/2. So one thing I could say is that 2 cosine theta is equal to that guy. So if I use that expression, I can rewrite this up above as e to the negative 0.5t times 2 times negative 1.7075 times cosine of 1.3229t, like so. All right, so this term has been collapsed into a term that is truly a real thing that we can observe in the real world with no complex exponentials. Now this guy looks very similar. I have e to the j something t minus e to the minus j something t. That looks very similar to this, right? Looks very similar to that. But the difference I have is I have a j multiplying here, and here I have a 1 over j. So there's a couple of ways to look at this. One way would be to say, well, what happens if I multiply this expression by j over j, right? In other words, multiplying by 1. So if I did that, I have j times j on the bottom, which gives me a minus 1, and I have a j on top, so I get minus j over 2, right? Minus j over 2 e to the j theta minus e to the minus j theta, like that. Now, I kind of sort of have a similar relationship up here. I'm going to say that instead, let's multiply minus 2 by both sides, right? So I get minus 2 sine theta equals j times e to the j theta minus e to the minus j theta. Okay, this exists here. Okay, so I'm going to write this now as minus 2, because of that, the way I manipulated this here, minus 2 times 0.6133 times sine of 1.3229t. And that is my full expression for the transient response. So if I go back to my full y of t must be e to the negative 0.5t times 2 times minus 1.7075 cosine 1.3229t minus 2 times 0.6133 sine 1.3229t. And then I have to add to that the particular solution, and I'm just going to again write that as b cosine t plus phi. Okay? Now, one thing to notice about this transient response. The transient response, as I said in our very first lecture on differential equations, basically tells us, or it exists, basically because the circuit itself, or the system, basically is trying to resist the change in energy storage. So if it's got inductors and capacitors, the capacitors are trying to resist changes in their voltage, and the inductors are trying to resist changes in their currents. Okay? Over time, this transient response better disappear, and it does, and the reason it disappears is because this e to the negative 0.5t. As time advances, this multiplier here goes away, and this term completely disappears. Okay? All right, so what I'm going to do is I'm going to try to plot that now in Matlab. Okay? So let me make this smaller. All right? And just so I remember, this is the guy here that I want to plot. Okay? And here's my Matlab code for that. Okay? So notice I defined something here. I wanted to have a range over which to plot. And I decided to plot over 3 periods of my transient response. I want to be able to see what's happening here. So what I did was I defined a variable omega c, which is 1.3229. So basically it's the frequency of my cosine and sine terms over here. All right, so I did the period is equal to 2 times pi over whatever that frequency is, okay, omega c. And then I did 1,000 points in a period here for 3 periods. And then I said y sub c is equal to this guy, right? So y sub c is this response. Now let's unpack this guy a little bit here. So y sub c is that. So basically I took everything that we found over on this side. All right. Now notice what I did. I have a dot multiply here. So I dot multiplied this sine cosine thing by the exponential e to the negative 0.5t. Because sine and cosine are going to give me a whole bunch of results, basically one value for each point in time, and exponential is going to give me one value for each point in time, I have to do the element-wise multiplication. Okay? And then I do my yp, my particular solution. Okay? My particular solution is very simply, right, in this case I did omega times t, and you'll notice that I defined omega up here as 1. Okay, so the only other thing I did was I took my phi and I multiplied by pi over 180. Okay, and then you'll see what I did was I used a subplot to basically plot for me. On the top I'm going to plot the transient response, y sub c. Then I'm going to plot the particular solution in the middle, and then I'm going to plot the total solution on the bottom. So notice with the subplot command, what I did was I said 3, 1, 1. What that says is I want 3 plots total, and the plot that is in the very top is the 1, 1. So basically it says in the first row and first column, I want to put this particular plot. And then in the second row, I want to put in this particular plot for the particular solution. And then in the third row, what I want to do is I want to put in the total solution. So let's go ahead and plot that. So I'm going to basically highlight all of that, and I'm going to say evaluate selection. And there is my graph. Okay? Now the top here, I didn't label my graphs, I should have, right? My top is y sub c. This is the transient response. Now let's look at this. This guy looks a little bit funny. He starts down here at negative 3.415, but I see that he decays to 0 over time. Right? Basically that value is getting super close to 0 as I get over here. Here's my particular response. Okay? Basically just a cosine that's shifted. And then I have my transient response, which looks a little bit funny there at the beginning, but eventually begins to look exactly like my particular solution. The reason this guy looks funny in the beginning is if I looked at this, this is the particular solution. At time t equal to 0, that looks like he's about 3.44. This guy should be about negative that, right? So that the total solution is basically equal to 0 at time t equal to 0. Right? So it matches what our initial conditions say. Now, one thing that's a little bit deceptive here is you'll notice when you plot in Matlab, it just automatically scales these axes. So if you look at this, one thing that's a little bit goofy is it's saying the bottom 2 graphs go from -4 to 4. This guy goes from -4 to 2. So when you first look at this, it doesn't necessarily look like this guy is tending towards 0, because your mind is probably used to thinking, well, 0 is in the middle somewhere. So one thing that's good is to tend to put these all on the same axes. So one thing I'm going to do now that I know that, I'm going to say here, I'm going to rescale my axes. I think it's axis. Let me see. So I'm not sure. So I'm going to type help axis. All right. Control axis scaling and appearances. So axis, x-min, x-max, y-min, y-max sets the scaling for the x and y axes. All right, so I want to use that command. And come back. There we go. So I'm going to set this guy like so. I actually don't want to change. So I'm going to say from 0 to the last value in the t vector, so 3 times t. And then I want to say I want to go from -4 to 4 on the y-axis. Just for good measure, I'm going to tell all 3 of these guys to do that. And go. And it didn't listen to me. Let's see. Okay. Why is it not listening to me? I know why it's not listening to me, because I've violated a Matlab rule here, which is to say that before I do this, I should type hold on and then hold off. So the hold on command basically makes it keep whatever was there when it runs the plot command. Okay, so I'm going to type hold on. If you look at chapter 3 in the book, it talks about this. All right, so now there we go. All right, so now I can see a little bit more clearly this guy's going to 0 than I could before. Okay, all right, hopefully that helps to explain a little bit more about how to solve these problems.